All right, take 4. So this is chapter 19 of the material science textbook, which is thermal properties of materials. So understanding how heat affects the materials they're using is an important part of an engineer's job. So far, we've looked at what's happening in the microstructures of materials and their intrinsic properties. And in this chapter, we'll be looking at how changes in temperature affect or influence materials' behavior. After this chapter, students should be able to define heat capacity and specific heat, note the primary mechanism by which thermal energy is assimilated in solid materials, determine the linear coefficient of thermal expansion given the length alteration that accompanies a specified temperature change, define thermal conductivity, and note the 2 principal mechanisms of heat conduction in solids. So first we'll be going over some important definitions and concepts. Materials respond to changes in temperature in several important ways. One of the most common effects is thermal expansion. How much a material expands or contracts depends on its linear coefficient of thermal expansion, its initial length, and the change in temperature. When heated, particles in a material gain energy, causing them to vibrate more and move further apart, causing the material to expand. Another important property is heat capacity, which represents the amount of heat required, or the amount of energy required, to produce a unit temperature rise. It's usually specified per mole of material. So joules per mole times Kelvin, or calories per mole times Kelvin, which is just temperature. Heat is transferred through materials primarily by 2 mechanisms: phonon lattice vibrations and free electron movement. The relative importance of these mechanisms varies between metals, ceramics, and polymers. And finally, ceramics are inorganic, non-metallic substances such as porcelain, glass, tiles, bricks. They're very hard, brittle, and heat resistant. A phenomenon known as thermal shock can happen when ceramics are subjected to quick changes in temperature. Other key terms or concepts that we'll be going over later are, as per mentioned already, heat capacity, specific heat, thermal conductivity, heat conduction, thermal diffusivity, thermal shock, thermal expansion, linear coefficients of thermal expansions, volumetric expansion, insulators, thermal stress, conductors, melting temperatures, coefficient of thermal conductivity, and phonons, among other things. Okay, so our first definition is going to be heat capacity and specific heat, or specific heat capacity. So first, we're going to cover heat capacity. So heat capacity is the total amount of thermal energy required to raise the temperature of an entire object by 1 degree Celsius. Or it can be different units of temperature, but the amount of energy it takes to raise it by 1 degree. So this one depends on how much material the object has. So it's specific to its size, so it's kind of hard to compare between different materials if you don't know their size. Specific heat tells us how much energy is required to raise 1 unit of weight. So like raise 1 kilogram of material by 1 degree Celsius. Not of weight, it's of mass, but it's how much energy is required to raise a kilogram or a gram of material by 1 degree. Why these matter? So different materials absorb heat at different rates. For example, like my lovely demonstration shows, water in this kettle, water has a higher heat capacity, so it is slower to heat up. Oil, on the other hand, has a lower heat capacity, so it is quicker to heat up. So if you had the same mass of oil and water, oil would heat up quicker, which means that water takes significantly more energy to heat up than the oil would. So this is one of my examples in my written notes. But if we have 1 kilogram of aluminum, 1 kilogram of copper, and we apply the same amount of thermal energy to them, the copper will rise in temperature much more. This is because aluminum's heat capacity is higher, around 900 joules per kilogram K, while copper's is roughly 385. This concept is important to note, especially when materials being used in real world setting are subjected to different changes in temperatures, and we need to understand how quickly they will heat up based on how much energy is applied to them. All right, next topic. We're going to talk about thermal expansion. So when a material is heated, the atoms vibrate with greater amplitude, which means they gain kinetic energy from the thermal energy added. They start to move around more and they start to vibrate more. As this happens, the average space between atoms increases, which makes the material expand. This is called thermal expansion. So the first thing we need to understand is the linear coefficient of thermal expansion, which is just part of the formula for thermal expansion, which is change in length equals alpha, or the linear coefficient of thermal expansion, times the original length times the change in temperature. So this tells us how much material expands per degree of temperature increase per unit length. So it's extremely material dependent and dependent on the original length present with the material. Also, what we're talking about, or what we're going to talk about, is volumetric expansion, which is pretty much the same thing just for 3D objects. So this one is change in volume equals beta, or which is just 3 alpha for most types of solids, times the original volume times the change in temperature. So this one is pretty critical when applied to real world scenarios, because lots of materials in buildings, roads especially, expansion joints, there's expansion joints in buildings. It's very important because materials need to be allowed to expand and contract, especially here in Fredericton, where we have very contrasting seasons where it can either be really cold or really hot. So materials need to be allowed to expand or contract in a controlled way, and we need to understand when they're going to do that. All right, the next topic we're going to talk about is thermal conductivity and heat conduction. So this is basically how well can a material transfer heat through itself. So if one side of material is hotter than the other, heat flows from the hot side to the cold side, which is almost like anything where high energy spaces want to travel to lower energy spaces, which is not the best word for that, but I'm going to go with it. So thermal conductivity tells us how fast that heat moves through the material. So the equation which applies to this is Fourier's law, which is Q equals negative K in parentheses delta T over delta X. So Q is the heat flux, the rate of heat transfer per area. K is the thermal conductivity, which is a constant for specific materials. And dt over dx is the temperature gradient. A higher K value means the material transfers heat more easily. Now we're going to be talking about the relative values of thermal conductivity in the 3 main types of solids, which are talked about in this chapter, which are metals, ceramics, and polymers. So metals generally have the highest thermal conductivity because their free electrons carry heat extremely efficiently. Ceramics have moderate conductivity. They rely mostly on lattice vibrations, and polymers are usually very poor conductors because their molecular chains don't transmit heat well. Which leads into our next point about heat conduction mechanisms in solids. So the first type, which we kind of mentioned before, is electron transport. So in metals, heat is conducted mostly by free electrons. These electrons move fast and can transfer energy extremely efficiently. And the other kind is phonon transport. In ceramics and polymers, heat is carried mostly by phonons, which are basically lattice vibrations. So phonons transmit energy by vibrating from atom to atom. So these are the 2 primary mechanisms of heat conduction: electron conduction and phonon conduction. All right, the final topic we're going to cover is thermal diffusivity, a concept that actually confused me when I was trying to learn this, because it's closely related to thermal conductivity, but not quite the same thing. So thermal diffusivity measures how quickly a material's temperature changes in response to a change in heat. It's essentially how fast heat can spread through a material, take into account both how easily heat moves in the material and how much heat the material can store. So the formula for this one is the ratio of thermal conductivity to the product of density and specific heat capacity. So it's K over the weird P times the specific heat capacity. So high thermal diffusivity means heat spreads quickly and the material responds fast to heat. And a low thermal diffusivity means the material changes temperature slowly. So the internal temperature persists longer. Okay, so let's solve the problem of thermal expansion involving a steel beam and a concrete beam. So the first thing we're asked is, which material would we expect to expand more when it's heated from 20 degrees to 40 degrees Celsius, and they're free to expand. So basically this one's just kind of theoretical and understanding that steels typically have higher coefficients of expansion, or coefficient of linear expansions, and concrete would typically have lower ones. So we would expect the one with the higher coefficient of linear expansion to expand more. Thus, the steel beam should be the one to expand more. And then we are asked to calculate the coefficient of linear expansion in a steel beam if it is stretched from 6 meters to 6.002 meters. So the equation we're going to be using is delta L equals alpha times L aught times the change in temperature. So our change in length is going to be our final length, which is 6.002 minus 6 meters equals alpha is unknown, original length 6 meters, and our change in temperature positive 20 degrees Celsius. So we're going to bring in our calculator. On the left side of the equation, we're going to have 0.002 equals alpha. We can bring those two over to the left side. We will have 6 times 20.002 divided by 6 times 20 equals 1.6 repeating times 10 to the negative 5 equals alpha, or the coefficient of linear expansion. And this is pretty close to a typical coefficient in low carbon grade steels. So we can assume this to be the correct coefficient of linear expansion. Right. With this example, we are going to be talking about thermal conductivity. So as you can see here, we have, maybe I'll get the point out. We have our nice outside. We have a layer of brick, which is 0.2 meters long. We have a layer of insulating foam, which is 0.1 meters long, and the indoors is positive 20 compared to the outdoors. What we want to find is the total change in temperature which occurs across each material. Another important thing to note is the thermal conductivities of the brick and the insulation foam are 0.72 and 0.04 respectively. Alright, so what we should note primarily is that the heat flux between the two layers is going to be the same. So this is our equation. We have heat flux is Q, K is the thermal conductivity, obviously change in temperature, and that is over the thickness of the material. So since we decided that the heat flux is the same, or is equal between the two layers, we can say Q of brick equals Q of foam. Thus, we can sub in our equation, which is K brick delta T in brick, that does not say brick, over the thickness of the brick equals K of foam, delta T of foam over the thickness of foam. So, since we are looking for the change in temperature for one of them, we are going to set up the equation so that we will have one of them isolated on one side. So, let's say we want to find the change in T, the change in temperature of the foam. We can multiply L to the other side and divide the K of the foam, so it will go to either side. So we will end up with L foam times K brick times delta T of brick over L brick times K foam. And I'm going to take a quick break while I work this out. Okay, now I have worked it out. So we have plugged in all of our values. We get 9 times delta T brick equals delta T foam. And I think the easiest way to do this is to put delta T total equals delta T brick plus delta T foam. And then we can say for every one change in temperature of brick, there is 9 changes in temperature, which gives us a nice round number of 10 units in change of temperature. So multiply by 2 to match the actual 20 degrees, which is the change from outdoors to indoors. We can say that delta T of the brick equals 2 degrees Celsius, and delta T of the foam equals 18 degrees Celsius, which makes a lot of sense, obviously, since the insulating foam is meant to insulate and take up a lot of that temperature that's coming in from outside. Yeah. All right, to summarize, in chapter 19 about thermal properties, we have learned that materials respond to heat in several different ways. They store energy, heat capacity, conduct heat, thermal conductivity or thermal diffusivity, and they expand or contract, which is thermal expansion. From the examples, we saw that higher thermal conductivity or diffusivity means faster heat flow or temperature change, and materials with low conductivity take most of the temperature drop in composite systems. Understanding these properties is very important for engineers, and applying them to real-world scenarios can prevent critical disaster and are very important to understand. I hope you enjoyed this lecture video. Thank you for listening.